Good evening and welcome everyone to Simplex Pachinko. This is Obi-Wan Pez. And welcome to Math Night. We're here. And we're going to do whatever we feel like. So let me know if anybody has any requests out there. I did pop our ads stuff, so hopefully that'll prevent anybody from having to have pre-roll for an hour. Hope y'all are having a good week. I know it just started. So this week at school, we've been working on graphing, and particularly doing graphing for function transformations. We'll get there eventually. Brain's still working. There we go. All right. So basically, what I've been doing with my students is telling them that when we want to do stuff like how do I graph a circle? I go like this, let the thing fix it, and say, ta-da! But probably not your actual question. So such perfection, much circle. Yes, I definitely cheat here. If I were to actually shut this off, most likely the way that I would actually graph like our unit circle or something like that is we would know we have, wow, okay, there we go. Do something like this and say for this particular point here, we know that the four corners of that's 1.5. So the four like points that are going to be on the circle are going to be here. And then I just basically go very carefully like this and hope that I get it. Yeah, with equations. So circles are part of a group called conic sections. And conic sections include stuff like, well, lines, points. So those are the real easy ones. So points and lines, and then parabola. And actually, I should bump that down one. points, lines, circles, ellipses, parabolas, and hyperbolas. Guess we'll go with parabolas as well. Now, all these things have something in common when it comes to their equations. I mean, points are just points, so they don't have an equation by themselves. But lines, you get your typical. No, hang on. We'll get there. So lines look like ax plus by is equal to c. Parabola, you're probably used to seeing at least somewhat. The most basic parabola looks like ax squared plus by equals c. The circle is going to be ax squared plus ay squared equals c. So those have to have the same value. And actually we just eliminate the other letters, it's fine. So we don't need the a actually. Alright, so x squared plus y squared equals r squared. And that's one we're going to see all the time in this setting especially. Ellipses. Oh, are we not? Not one of those that were. No, there we go. So this is an ellipse. It's basically just a circle that's looked at from a different angle, or one that's been kind of squashed. So ellipses have ax squared plus by squared is equal to c. And hyperbolas are ax squared minus by squared equals c, or negative ax squared plus by squared equals c. Where for all these a, b, c, and r are all going to be positive values. So then we can define these. So if you were to take a like piece of clay, and I've actually seen this before, it's really awesome. But if you take a piece of clay and you mold it into a perfect cone, like as best you can. If you have a potter's wheel, it makes it way easier. But yeah, so mold clay into a perfect cone. And then they have these little like garrote wires. I hate to say it, which they use for clay, which basically you just stick the wire on the clay and pull, and it slices right through it. So if you were to create... Really? Man. Alright, fine. Let's go back to enhance ink shape or whatever. There. So if you were to take a piece of clay and you were to mold like a perfect Megalomorph ellipse out of, or no, whatever, perfect cone out of it. Where do we want this? We want that to be right there. Okay. So the taking cup. Yeah, we're not playing that game. Right, we can see all of that. That's fine. So if we start with a cone, and if you were to make one out of like perfect clay, and then just take a plane, or in this case, one of those little wires for clay, and you slice it through, you can make all of these individual shapes. So if you slice directly across like this, then this is actually, if you look at it from the top down, it's going to make a perfect circle. All right, provided that you made a right circular cone. What the hell? Excuse me? No. That was weird. Just like my own phone tried to dump me. Maybe, whatever. I don't know. Sorry. So yeah, if you take your right cylindrical cone and you slice just straight across it, you end up getting, it looks like an ellipse from this side, but again, it's going to be a circle if you're looking at it top down. And then if you take this and you slice it at any diagonal, wow, that is not even close. Go like that. Slice it at any diagonal, which is not itself I know what I was thinking. God, man. Oh, we're having a good day already. Anyway, slice it at any angle that allows it to cut through both the top somewhere here and the bottom somewhere here. So when you do that, here, let's cut this down a bit. We'll end up with this actual elliptical shape. And again, the face of the clay that you've just cut is going to have this elliptical shape to it. All right, then if we go further and we go slice it at an angle which is greater than the angle at which our sides are rising, then that is slightly greater. We get something like this. But the problem with this particular one is that it actually goes into the floor. So if you slice this way, what's going to happen is that this actually follows the path of the outside of the cone. And it never quite makes it back to the bottom. It never starts closing in again. So it's just going to continue going out further and further and further and further, here and also here. So this makes a parabola. So we get a circle here, ellipse here, parabola here. We also get a line if we just take it and notice that the side of the cone is itself a line. Likewise, the conic section created by the intersection of the two lines gets us a point. All right, then the fun one. If you go and take your, just a standard lamp with a circular lampshade on it. Oh man, you guys are gonna see the horrible stuff that's all over my room. Make sure nothing's gonna dox me here. All right, here we go. Let's do that. So, we hold. We hold the lampshade to a wall. It's producing a conical sort of shape, and then when it intersects the wall itself is going to produce this shape, which then goes out further and further and further. It doesn't, unlike a parabola, it's not going to go downward faster and faster and faster. It's going to steady out at the same angle that the lampshade is from the wall. And we could also do it for the top as well. All right, let's just go back here. Y'all can come back. All right. Awesome. Perfect. Perfect angle. Okay. So when we create, when we end up hitting a lamp, pointing a lampshade at the wall and making light bounce off the wall, we can see that it's going to basically hit at this point, and then the one side is going to go up like this, and eventually it's going to match this angle here is going to match this angle here. So it's going to go up at the same rate as the side. And then on the other side here, it'll also do the same. This is on the back side. That's not what I want. Let me try again. Okay. The plane that we're going to use for this is going to cut kind of diagonal through. And this is going to create a vertical cross section. Yeah, that's my problem. Okay. I'm cutting this at an angle rather than like straight back. So the plane that's cutting through it is kind of like this way. So it's going to end up making some sort of angle like this. And like that. And in doing so, because it's going to essentially be vertical, this is also, well, it is vertical. It's also going to cut through the bottom in exactly the same place, which I totally messed up. It's fine. It's fine. This is then going to kick out this way, and again, kick out this way. Oh, you know what? It shouldn't be on the edge. That's why. Right? The point that this actually hits should be like way in here, and that's why it should be like that. Alright, so then this one coupled with this one are what are called a hyperbola. That is not what I wanted. So these also have special properties. Alright, so let's go back here. Look at all the other crazy messages here. Yeah, Blamelin. Yeah, vector calculus is crazy. Yep. Yeah, Megalomorph says if we try to make an ellipse, something like this and like that, right? Whatever sides they might be, it doesn't really matter. And this is going to end up, if we try to find the perimeter around this thing, we're going to have some problems. Now, why on earth will we have problems with that? Well, so for this, if we're going to try to make a an arc length integral out of this, so arc length is going to be equal to the integral from a to b of the square root of, I can go either way with this, but all right, 1 plus f prime at x squared, where this function f needs to, well, first of all, it needs to be a function. And so with this, we're going to have to do half of the ellipse. So just the top half of the ellipse would have an equation if we centered it at 0, 0, just to make things easier. So mean that f of x, we would have to have x squared plus y squared equals 1. Divide each one by its individual semi-major axis or semi-axis measurement squared. So our x distance is going to be 4, makes that 16 on the bottom here. Our semi-minor axis is 3, square is 9. If we want to get y by itself in order to get f of x, we're going to move this over. It's going to be 1 minus x squared over 16, all multiplied by 9, and then we take the square root of all that is equal to y. Again, we're only going to be doing the positive one, so absolute value of y, it's just going to be positive. Here, that means we're going to be taking the derivative of this first. And yeah, this can be a bit of fun. Calc 3 started with vector calc. Series week 3. Yeah. I mean, this is kind of just how your particular school is doing it. And everybody does it a little bit differently. When I taught differential equations, probably about 2 years ago, I decided on the day that I did it, on the day that I got to this particular topic, I watched a video from one Dr. Pavel Grinfeld, and he was doing he was using linear algebra to describe how to do differential equations and interconnecting something. I don't even remember. It's been so long since I watched this. He was doing a partial differential equations class, but he like reworked everything so that immediately following unit 1 in differential equations, which is like how to solve first order linear differential equations, the second thing you do is linear algebra. My course, when I took it, and most of the time that I had been teaching it up to that point, I had been doing linear algebra had been unit 3. So it was the last stuff you did in the course. So we would do second order differential equations next. And then I was like, well, this is really interesting. And Dr. Grinfeld did this thing where he was just like, okay, let's talk about linear algebra. And he went straight from, first order linear differential equations directly into linear algebra. And, oh, by the way, you can use this to solve both first order differential equations in systems as well as second order differential equations as, you know, one thing. And something just clicked in my head, and I was like, I want to do this. And so this was about 15 minutes before class. It was terribly irresponsible, and I went and told my students, all right, look, this is what we're doing. It's an experiment. I have no idea if this is going to work or not, but it's going to be exciting. And I think they liked it enough that it did not bother them too much. It was a little crazy, but I think it worked, and they seem to at least understand most of it. Oh, and then I got a call today from, email. I got an email from one of my old students. He's coming back to see me on Friday. I was like, yeah, absolutely. Anytime you want to come back. All right, so here, y prime is going to be equal to, we have the, all this stuff raised to the 1/2 power. So 1/2 times, this is going to be 9 minus 9x squared over 16 raised to the negative 1/2 is going to be the derivative of the main portion. And then we have to multiply by the derivative of the inside, which is then going to be negative 9/8 x. Yep. That's going to be a negative 9/16 x times 9. Well, we could just pull out the 9. No, we can't. Careful. I mean, we can pull out the 9, but you have to take a square root and all that. So, it's fine. 9x squared over 16 raised to the negative 1/2. Alright, then that arc length equation is going to end up being go from negative 4 to 4 or twice integral from 0 to 4. We could also do that, right? Because ellipses are symmetric, so we're allowed to do that. All right, square root 1 plus this stuff squared. It's going to be 81 x squared over 256 times 1 over. This square root is now gone. It's just going to be on the bottom here. 9 minus 9x squared. I'm glad I didn't fiddle around with that. It's 16. Now we can pull the dx. Oops. Okay. Twice integral from 0 to 4. Square root 1 plus 9 from the bottom pulled out will make this a 9x squared divided by we're gonna have to multiply well, just multiply 256. So this is gonna be 256 minus 16x squared. Dx on the outside. Why would you do this? Alright, Megalomorph, stop me if you've seen a student do this before, because I'm sure they have. Oh, no, no, no. I see. I was gonna try to be clever here, but being clever is part of the problem. So in theory, pull a square root 1 over 256 minus 16x squared. I'm sure this does not work entirely at all whatsoever, but square root 256 minus 16x squared plus 9x squared. Alright, I just needed to separate that for a second, so it's not a big deal. But this is going to be 256 minus 7x squared over 256 minus 16x squared? Question mark? I think that's the cleanest I can make it. Which is beyond ugly. But nonetheless, I think that is the cleanest that I could make it. Did I get dropped? It's possible people just left. That's fine. I was helping the kids with model rockets today, and I dropped a little bit of Gorilla Glue on my finger, which yeah, I don't know if you've ever done that with super glue or Gorilla Glue or whatever, but yeah, it's some nasty stuff. I now have this shiny spot where it, and it's also like hard, where I've kind of like melted the skin and apparently tried to fuse it with plastic, so that didn't go well. But yeah, the top layer of my skin is now, it's just a little tiny dot. It's not a big deal. It's still annoying because now it's there and I can feel it. Oh. Uh-huh. No, it didn't tear the skin off. Nice. It was just... I'm usually used to, you know, super glue essentially melting your skin and bonding it. Oh, good. That's nice. I don't have to worry about that anymore. Anyway, I think this is the nicest that I can make it, which is still unsolvable, but it's at least something that, you know, I could, in theory, work with. All right, so going back to the beginning. So if anybody is stopping in, you know, welcome. My name is Obi-Wan Pez. This is Unsimplex Pachinko. We are going to be talking about function transformation and my particular formulation of how this all works. All right, sorry about that. So here we're going to look at function transformations. If we're going to look at, unfortunately, conic sections are not going to be good for the functions that we're using. So generally speaking, we're going to be talking about, you know, functions first of all. So doing a circle is not going to be a function. So function transformations are going to look like y equals a times f of b times the quantity x minus c plus d. So generally they're going to be of this form. Again, f could be any function that we want to use. Real valued. So any real valued function we want to use. Stuck on the garbage can. All right. So the way I did this was we started out with set of axes like this. And if we're going to talk about function, what I would want is to first talk about parent functions. So parent functions are going to be the building blocks of everything we talk about. This is just going to be y equals the function itself. So you're going to do something to it. You're going to do something to x, which is going to be one thing and one thing only. And all of the like categories of things you can do to a function will be their own separate category. So, for instance, the most basic parent function that exists is going to be y equals, I would say y equals x, technically. There is also like y equals a, but it's just a constant, and then it doesn't really do anything for us, so we're just going to leave this one out. Say, y equals a isn't going to count for us here. Or y equals 0 or anything like that. But the most basic function that actually does something is going to be y equals x, and this has our nice little graph that we're used to at this point. Which, as we go over to the right, it's going to go up, and every value that we plug in for x, we're just going to get that same value back for y. So 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, etc. We'll go like that. And then naturally going in the other direction, I'm going to get -1, -1, -2, -2, -3, -3. And also, I hate it. Thanks, I hate it. All right. Fine, you don't want to do this? We'll just go like this. Go make the exact same line that we had there, and then we'll fix our points. Something I tell my students, you make the points big enough, no one will ever notice. Alright, so we get our function y equals x that looks like this. And again, if we want to do like our table of values for y equals x, this is just going to be -3, -2, -1, 0, 1, 2, 3. And for the y values, you literally just get the same thing. So this is terribly boring, but it makes a real easy basis to start all this stuff on. All right, then my next move was to say, okay, this is all cool, but then what about if you do something like y equals x plus 7? Well, in y equals x plus 7, let's do that. I'm going to get values. In y equals x plus 7, we end up with values which, again, start with the initial x values that we had up above. And then here we say we're going to take all of those x values and add 7 to them. So -3 plus 7, we're going to get 4. -2 plus 7, we're going to get 5. -1 plus 7, we get 6, 7, 8, 9, and 10, corresponding to the same x values on the other side. So where does that put us? Well, this is going to be, let's see if I can move this slightly. Hey, that's better. All right, so, all right, so if we count every 2 as a point, or as our whole values, all right. We got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. I'm zoomed in really far so that we can actually see this. When I zoom out, you're just not going to be able to see anything in here. So apologies, sort of. Anyway, marking these points, we end up with, again, 0, 7. Okay, out to 3. 2, 9, 3, 10, 1, 8, 0, 7, -1, 6, -2, 5, -4, 4, -3, oops, -3, 4, -4, 3, -5, 2, -6, 1, and -7, 0, and -8, -1, -9, -2. We'll go like that. Then mark straight through these lines. Straight through these points. And straighten them out just a little bit. All right, so we've got points here. This goes through 0, 7. We go through all these points here, which include -3, 4, and all the other ones on here, and eventually to -7, 0, and -9, -2. All right, so when we look at this, you can see this nice pattern. We can see that our vertical value, we started with this point here. Really? There we go. Started with this point here, which was originally at 0, 0. And then by using this transformation and saying, we're going to take the output of this function, y equals x, and now what we're going to do is alter it so that it becomes y equals x plus 7. Let me use this for consistency. This one's going to be f of x equals x. Just that. All right, so y equals this function here, f of x plus 7. So y equals f of x plus 7. Okay, so this takes the y values that are coming out of the function, our f of x up here, and f of x here, takes those y values and adds 7 to them after the fact. So then we get all of these values here. that causes all of these values to be pushed upward 7. So you get these values here. These used to be much lower. Again, this used to be down here somewhere. Alright, that was 4. 1, 2, 3. Yeah. That point used to be down there somewhere. And now it's been moved up 7. Now we could also say, well, who's to say that this had to be f of x plus 7? It could also be that this wasn't f of x plus 7, but rather y equals f of x plus 7. Since the identity function that we're using, y equals x, allows for these values to be either inputs to this particular function or outputs to this particular function, we're allowed then to just say, well, why not make it this? Perfectly possible. All right, what does this do? Well, it's going to take our x values and it's going to make them 7 larger before putting them into the function, before finding out what its function value is. So this does something a little bit weird. If you look back at the original parent function up there, and we concentrate on 0, 0. All right, we want to know now what value for x is going to get us a 0 to go into the function. So one way to do this is we say, like, okay, this is x plus 7, and this is our y equals f of x here. So x plus 7 is going to be what we put into the function, and therefore x plus 7 needs to be the same stuff we had, -3, -2, -1, 0, 1, 2, 3, at least, you know, for ease of whatever we have up there. Our function values are just the same stuff, so -3, -2, -1, 0, 1, 2, 3, just the same. Then this is no good, because we don't want what are the values for x plus 7. We want what are the values for x. What are the points that we're putting on this chart? So in order to do this, we have to translate this back to just x. Well, how do you translate it back to just x? Okay, subtract 7 from everything in this column. So if we subtract 7 from everything in this column, this gets us -10, -9, -8, -7, -6, -5, and -4. So now we have to read this as these are our x values for these points, and these are our y values for these points. These y values right here go in there. These x values here go in there. So what has it done this time? Because it hasn't moved everything up. Instead, what it's done is it's taken all of our points and it's moved them to the left. So we say that here, our point which used to be at 0, 0 is no longer at 0, 0. Our point at 0, 0 has now moved to -7, 0. So -7, 0 is alternatively a new origin point. I didn't bring that up first. That should have been, I should have brought that up first. All right, so I'm focusing on our point 0, 0 from the original parent function and calling that the origin point naturally, right? Because it's sitting on the origin in the parent function graph. The origin point is always 0, 0 in all parent function graphs, even if the function does not go through it. We can talk about that. Then, when we start shifting stuff around, right? We said that y equals f of x plus 7, adding 7 on the outside of the function, shifted it up 7. Adding 7 on the inside of the function is actually going to shift left 7. So here we're taking this original origin point that used to be at 0, 0, and we're shifting it back to negative 7, 0, right? It's up to you which one you do. It could be a shift up or it could be a shift to the left. Doesn't matter to me. All right, and then here's the important thing. This pattern that we had here now is not a pattern of what points you have, but rather it's a pattern of distances. From the origin point, from the new origin point. All right, anyway. So yeah, we've got all of these points from the original parent function are no longer going to be just points that you get. They're now going to be the distances that we're going to use for all of this stuff. So all this means is that if all you have is a shift, then what you're going to do is say, here's my new origin point. Now I'm going to use the exact same distance scheme. So, you know, to the right this far, up this far, to the right this far, down this far, whatever we're doing. So for the parent function y equals x, this is nice and easy, right? It's just over 1, up 1, over 2, up 2, over 3, up 3. Left 1, down 1, left 2, down 2, left 3, down 3. It's just going to go from there. All right, so parent functions come in all shapes and sizes, and we know most of the other parent functions as polynomials or power functions, which are going to look, roughly speaking, like f of x equals x to the nth power. And generally speaking, we can also make this x to the b power, where b is just any real number, or n is particularly a positive integer. Doesn't much matter, we can do anything we want here. Generally, power functions are positive real numbers as well. All right, so polynomials and power functions are like that. We've got roots,
x to the m over n, where m and n are going to be integers, and n is not 0. Rational. P and Q are polynomials. So the most basic rational functions that we have are going to be f of x is 1 over x, and f of x is 1 over x squared. So most basic ones we have. Roots, again, we're going to get most basic. F of x is the square root of x, and f of x is the cube root of x. Okay. Root rational. Exponential. Where we get f of x is equal to some number raised to a power, or raised to an x power. So 2 to the x is good enough one to work with, and logarithmic. F of x is equal to log base b of x. And again, log base 2 is the most basic one we use. Although I do much prefer graphing, or no, I prefer graphing whole numbers, but I much prefer using natural logs just because it's easier to write it as like a quick little loop. I had a spider crawl down my leg earlier, and now I'm paranoid. So looking at these parent functions, we can come up with, again, the most basic ones. So if we wanted to do, for instance, y equals 2 parentheses x plus 1 squared minus 3, we'd want to say, okay, the parent function is going to be y equals x squared. Right, that's our shell that we're using here. And then we want to know, what does that parent function look like? What's it graph as, etc. We already know that this is a parabola. Again, 1, 2, 3, 4. We don't need to go out that far. So 1, 2, 3, 4. 1, 2, 3, 4. 4. Right. 5, 6, 7, 8. And we'll have all those. Alright, so a standard y equals x squared parabola is going to have a point at 0, 0, at 1, 1, 2, 4, 3, 9, 10, 11, 12, 13, 14, 15, 16, and 4, 16. Ish. Nope. Oh my god, come on. Alright, close enough. It's going to be copied in the other direction. So negative 1, 1, negative 2, 4, negative 3, 9, and negative 4, 16. That's much better. Okay, so this is the original parent function. Again, we have our origin point at 0, 0. And generally, I also call for an initial point. Which I call it at 1, 1. For Drixfit? Let me know what you would like to be called. Welcome in. This is pre-calculus, so generally speaking, we're talking like somewhere in the high school area, roughly speaking. I'm talking particularly about how I do graphing slightly different than other people, and how it changes things a bit. Alright, so we're going to go like this. That, yep. I am right in the way. Cool. Alright, we'll try this. So, welcome on in. My name is Obi-Wan Pez. This is N Simplex Pachinko, and we're doing some pre-calculus. So, the way that I'm doing this here, we want to graph this function. Our parent function, the one that we're modeling this after, the one that has been transformed, is that f of x is equal to x squared. So it's our basic parabola. And what I have done here is that I have said we have our standard pattern for parabolas, which is -3, -2, -1, 0, 1, 2, 3. And we actually go out to 4 as well, and -4, but that's fine. -3 is 9, -2 is 4, -1 is 1, 0, 0, 1 is 1, 2 is 4, and 3 is 9. So based on that, we have our origin point, 0, 0, which is here. We have our initial point, 1, 1, which is here. And then these 2 points are going to help us guide our graph to be able to say this is how we graph this particular function. So what I'm going to do is I'm going to come back up to the top, and say that based on what we talked about before with shifting, this term here is going to make all of our x values appear to be one larger than they actually are. Then we evaluate that new number on the function, and those function values get taken back to where we were. So the numbers that we're looking for x. The way that that works, again, in practice was we said, okay, if we're going to do this on a table, I would say I want my x plus 1 values in this particular function. And we want this to be not y, but rather f of x, because it matters for this particular case. In here, we want what are the f of x values that are coming out. But then it's going to change because we've got all this other stuff outside. So x plus 1 is going into the quadratic as -3, -2, -1, 0, 1, 2, and 3. We're getting out 9, 4, 1, 0, 1, 4, 9. Okay. On this side, all of our x plus 1 values, the nice numbers that we're plugging in to then square them and get our perfect squares. We want to now know what are our x values going to be, though. So in order to do that, we have to subtract 1 from all these numbers to just get x by itself. So this is going to be -4, -3, -2, -1, 0, 1, and 2. Up here we look at our f of x values. And again, f of x is just this portion. So I did that wrong. Hang on. So this is the term that's being squared. So we got here x plus 1. That's what goes there. And I didn't do this properly. It's not f of x. It's f of x plus 1. So this is the squares being output. Okay, so then we're taking f of x plus 1, and we've got to do order of operations on this. So what else do we need? Well, we need this 2 here, which is multiplying our values. And we also need this -3, which is going to subtract all of our values. And we already said before, this is going to cause a downward shift. And this is going to cause a leftward shift. So left 1, down 3. Okay, so by order of operations again, now we've got 2 multiplied by our function, x plus 1 squared. So twice f of x plus 1. So f of x plus 1 is this column, so now double it. This is going to be 18, 8, 2, 0, 2, 8, 18. I'm gonna need more room. Boo. Okay, there we go. Okay, there's that. Okay, and then this is going to be twice f of x plus 1, we're taking those next values, and then we still have to subtract 3 from them. So subtract 3, we get a 15, a 5, a -1, a -3, a -1, a 5, and a 15. So, one more time, this column here is going to get us all of our x values, and this column here is going to get us all of our y values for this particular transformed function. So right here, this is your x, comma, your y in these two columns. I don't like using this stuff, which is why I teach it differently. So all of our x stuff here, all of our y stuff here. This middle stuff we're not going to pay attention to if you're going to be talking about individual points, like where on the graph are these points. That being said, you have to do a lot less than half the work if you do this in terms of distances. Because in terms of distances, we've got these right here, our -3 through +3, and our y's got traded around like this.